Hello, in this final part of the tutorial I'm going to look at some specific examples of properties we've proved of machine ethics implementations. So all this work has been done in something called the MCAPL Framework, which stands for Model Checking Agent Programming Languages. This framework can be found on GitHub, and you can see the URL there, and you will find all the examples I talk about in the examples directory of the MCAPL Framework. So if you're interested, you can go and have a look. So the first example I'm going to look at is one where we are checking that our implementation of the underlying ethical reasoning was correct. This appears in a paper we did with Alan Winfield and others from Bristol Robotics Lab, and it's an extension of that early system he had where he was trying to prevent the human landing in the hole. Now, I said in that system there was a kind of utilitarian implementation of the ethics. In this system we did something much more explicit, and in fact we took Asimov's laws of robotics as an example. So what happens here, as you can see in the diagram on the left, you have the H robot, the human, that is walking towards some danger area, which is that point A in the middle of the orange circle, and the E robot is supposed to be going towards some goal, which is the B. So if you remember Asimov's laws of robotics from your I'm sure, sci-fi reading, one of the laws is that you should obey rules given to you by a human. So there is an imperative on the robot to go towards B because it's been ordered to do so. However, an overriding rule is to prevent harm coming to humans, and it does this simulation like Alan's robots were doing in that early version, and it assumes that the person is moving towards this dangerous point A, and so it moves to intercept the person, and you can see the path of its intercept happening there. And in fact, it generates a number of candidate interception points, and these get judged by the ethical reasoning based on the 3 laws of robotics and some estimation of how likely the intercept is to be correct. The underlying system sends the candidates through to the ethical reasoning module, but it also has its own planner module, so it can reject all the options as unethical if it chooses and demand more ethical options get sent to it. So because we were mostly interested in this case in verifying that our implementation was correct, what we wanted to verify was that given the 3 laws of robotics, which are ranked, the system only broke the 3rd law if all other choices would break the 1st and 2nd law. It would only break the 2nd law if all other choices would break the 1st law, and it only broke the 1st law if there were really no options available that didn't break the 1st law. So this is it in logic. So that squared box is from modal logic, and in this case we were using something called linear temporal logic. So that square box means always, and we were comparing the options between 3 possible tasks. So this says if I believe, that's what the curly B means, if I believe my current task is plan 1, and P means it's perceptible, and in this case it means it comes from the underlying system calculation somehow, that task 2 is worse than task 1 according to RD. And so that's the 3rd law of robotics, the robot's obligation to keep itself out of danger. So you've picked task 1, but task 1 is actually worse than task 2 because it puts the robot in danger. Well, that implies that task 2 must have been worse than task 1, either in terms of obeying humans, the 2nd law, so that's RO, that means the robot is obeying its orders, or in terms of the 1st law, which is HD, that the human is in danger. So we verified that in our system, and in fact we put in 3 tasks, so it gets various orderings between these tasks. And it was always the case that task 1 was the current task, and it was worse according to the 3rd law. That was because the other tasks were worse according to the 1st and 2nd laws. We also verified this statement that always it picks one of the tasks. There were 3, it will always pick task 1 plus 2, task 3, and that turned out actually not to be true. We had to assume that these relationships between the tasks according to laws were transitive. So we didn't have any sort of cycles where task 1 is worse than task 2, and task 4 is worse than task 3, and task 3 is worse than task 1. So we put that in as an assumption, and then we were able to prove that. And then we had to go away and look at the way we'd actually implemented these orderings that were coming out of the underlying code, which was written in Python. And we used actually more traditional theorem proving techniques to show that we didn't have any cycles in those orderings. The next one I'm going to talk about is using the HERA system. And in this, that smart home example I had from the first lecture came out of this work, though it isn't actually in this paper, which we're publishing on this in AAAI in about a month. But in this, we had the HERA agent embedded in one of these cycles, these sense, reason, act cycles. So we do some perception, we do some inference about what's currently true in the world, and then we'd update the model that we had with new background facts. And actually we were quite interested here in whether we could actually update the kind of encoding of the ethics as well. So we would put in, change some of the utilities and things depending on what was going on outside to update that model, and then we would act. And those utilities which were changing were things like if we had set turning the lights on as -1 and it was now dark so people couldn't see, we'd take that to 0. So if we were using the principle of double effect, that wouldn't then be a negative if people actually needed to see. And for this one, I'm sure it will come as no surprise to you to learn that one of the properties we were trying to verify was it's always the case that if you believe there's a fire, then eventually, and that diamond means eventually, you'll perform an evacuate action. And that was the property I couldn't verify in that example I looked at earlier with the principle of double effect. We were also interested in sort of persistence over time of things. So we had this property we tried to verify in some kind of system that delivers messages to a user, that if it had a private message, then eventually it would deliver that message at a point in time when there were no visitors, or it was never able to deliver the message. So that's what that property below. And these are what I call sanity checking properties. They are things we want to hold in the system. We think they should always be true no matter what. And so we check that the way we've set up our encoding of the ethics doesn't violate these kind of sanity checking things that we think should come out of the ethics. Lastly, in this kind of scenario programming, so this is an example of some joint work that I did with Maria and also Matt Fisher and Matt Webster. And this work grows out of work that Michael and Matt had done in verifying the rules of the air, which are a code for how pilots should behave. And so they were trying to verify that an autonomous system would behave in the same way as a pilot. And when they'd done that, the Civil Aviation Authority in the UK said that's all very nice, but what happens when you're supposed to break the rules of the air because of some ethical override? And so in this one, we looked actually at a number of cases, and if you look at that paper, you can probably see examples in there of things that you call like implementation correctness. But for instance, we had a scenario probing example, and in that one, there's an aircraft still on the ground and its brakes have failed. And so this is a bit like a trolley problem. It can carry on moving in a straight line, in which case it risks colliding with a manned aircraft and obviously injuring all the people in it. If it turns right, it will risk damaging itself, and it might collide with some people who are to the right of the runway. And if it turns left, then it will damage itself again by colliding with some sort of airport hardware. And the ethical theory we're using here was based on prima facie duties. It's the same ethical theory that was being used by the GenF system, which I covered in the implementation survey. And in that we had an ordering between the duties. So the most important one was not to collide with manned aircraft, because this would kill a lot of people, followed by not colliding with people, followed by not colliding with airport hardware, followed by not damaging the aircraft itself. And in this particular situation, we just wanted to check that in the scenario we picked, it would turn left. This is the one that doesn't risk injuring any people. And so we verified this simple property. It's always the case that what the aircraft does, that's the D, is turn left. And that was correct. You can also use scenario probing for risk evaluation. And this is going back to this example of the human falling in the hole of Alan Winfield's. And we set up a really simple scenario here. There are two humans moving towards a hole that is in the center of the grid, and the robot is trying to get towards the goal, which as you can see is on one side of the grid. And so the robot predicts that the human are about to try and fall in the hole, and it will move to intercept them if it can find a safe path to do so. And it can only move in a straight line, but it can move anywhere on the grid in a straight line as one action. So in our normal sort of scenario programming way, we were able to prove that if the robot can find a safe path to the human and it believes the human is in danger, then the human will be prevented from falling in the hole. But one thing we're able to do with the MCAPL framework is export the models it creates of the system behaviour into other model checkers. And in particular, there's a model checker called PRISM that allows you to calculate the probabilities of outcomes over all possible execution runs through the system. So we were able to take this scenario out of the MCAPL framework, plug it into PRISM, and say, well, what is the probability that a human will fall in the hole given the kind of ethics we've implemented? And actually it turned out to be quite high, because just in the way we set this up, the robot often could not find a safe path to the second human, and so it wasn't able to get to them in time to stop them falling in the hole. So that's a very brief survey of the kind of things you can try and verify of a machine ethics system. And one thing, we want to say is a kind of important final step that often at the moment doesn't happen with machine ethics, is that not only should your system be ethical, but it's quite important that you can evaluate these claims that a system is ethical, and verification provides you with one route for doing so. Thank you.